Okay, so we start. So at first, we discuss the remaining sections of chapter 10 today. Then after that, we do our implementation of neural network. Then I discuss the some final presentations. So yeah. So I think all of you have already made one presentation, at least one presentation in applied statistics course, but just I want to make sure that you can see what are the points for final presentations. Do you have any questions so far for homework and last lecture or final projects? Okay, so we start. So chapter 10. Remaining sections basically discussed when neural network is useful and also how to estimate the neural network parameters. So I don't go into the details of technical details, but we need to know some algorithms to implement it in computer. So without any knowledge of estimation, you have hard time to see what parameters to tune. Okay, so I share slides. So we start from section 10.6. So when to use the deep learning or neural network? And deep learning does not always achieve the best result for prediction. Here's one example of hitters data. So remember that the hitters data have the 19 predictors and the salary of the baseball players for the next year. So basically the performance can predict future salary. And we only have 263 observations. And I think some erroneous observations, maybe actual, the sample size maybe is even smaller. But anyway, so 263 observations. And if we compare the performance of predicting salary of baseball players, the performance is this here. So we compare three models, the linear regression and lasso and neural network. So remember that lasso is basically linear regression, but we penalize the size of parameters. So basically it selects a kind of simpler model automatically. So linear model and lasso are both linear models, but the model selection procedures are different. And here, linear regression, this is just a full model. We have 19 predictors plus one intercept. So we have just full model. So 19 plus 1. And lasso, actually, 8 of the predictors have coefficient 0. So effectively, we have 12 parameters. And the mean absolute error for predicting salary is 254, maybe $1,000 for linear regression, and 252.3 for lasso. So it's slightly smaller. But the neural network, actually, it gets worse. So mean absolute error is the actual minus predicted. Maybe predicted minus actual is a better way to put. But anyway, we take the absolute value. So predicted minus actual. And take absolute value, then take summation over all observations. And R square is basically the sum of squares explained. So basically the squared statistics. So it's a kind of corresponding to mean square error. So it's slightly different measure. But anyway, any of this, even with this measure, the performance is worse than lasso, slightly better than linear regression, but the neural network does not perform well. And actually, if we fit the linear model with 4 hand-picked predictors, the mean absolute error is only 224.8. So it's much smaller. Yeah, so the neural network does not work. Yeah. So what kind of models to use? So one principle is when you face with several methods with similar performance, maybe, yeah, then we should choose the simpler model because it's more robust. And also, I think this is important, but most of the time, our data is small. Typically, if we do real world data analysis, the number of observations is between 30 to maybe 1,000. That is a typical size of the data set. But usually neural network works a large data set, at least maybe 5,000 observations. Hopefully they're 50,000 or 500,000. So usually neural network works only for a very large data, because unless we have very large data, usually we cannot detect very complicated pattern. If we only have 263 observations, even the truth is complicated, still the complicated model does not work well. And also, usually we need many predictors. Yeah, so theoretically, it's possible that the y is the fifth degree polynomial of x, but that is a rare case unless the observations are correlated. So usually the neural network is for very large n and at least a moderately large p. And also neural network does not give any interpolation. So we have parameters between noise and input, and also output and noise, or noise and noise. But usually we don't really interpret parameters. For example, parameters between noise, it's almost impossible to interpret that parameter. So neural network is good for big data and when the interpretation is not important. Yeah, and also my impression is the deep learning or neural network works good when the data is large, but also the algorithm looks complicated and cannot be expressed in words, but certainly there is a good algorithm. For example, the autonomous driving. So you are not sure what's the best principle for driving in general. It's obvious that when the signal is red, you have to stop, but the actual situation is more complicated. But we know that there is a good way of driving, and we don't know how parameters work, but we know that there is a good algorithm. So in such a case, the neural network is hopeful, promising method. And also image recognition. When you see a picture of elephant and a picture of hippos, you can distinguish it, but to be exact, you are not exactly sure. Maybe you are still, you can still tell the length of nose or something, but we don't know how to parameterize it. But in such a case, the neural network works great. And maybe examples that neural network does not work is, I think, for example, economic time series data. So typically the monthly data, so today, for example, CPI has been released, and monthly economic data, usually sample size is like 300. So 300 means 25 years. If we take data from older years, probably the economic structure was different from today's economic structure. So usually sample size is small. And suppose that you want to analyze the relationship between CPI and unemployment rate, maybe also GDP. GDP is maybe the quarterly, so maybe industrial production that is monthly. Okay, so these three have some relationship. Okay, unemployment rate can explain CPI, and the IIP also explains CPI somewhat. But this relationship is very noisy. And it's not that the quadratic term of unemployment rate helps to explain CPI, but we have more noisy data. We need some prior knowledge to transform or pre-process the data. For this kind of examples, usually the neural network does not work well. So we don't know what's the true relationship between unemployment rate, IIP, industrial production, and the CPI. We have just we want to explain CPI some way, but we don't know if there is a good algorithm or just data are noisy. So in such a case, usually the neural network that does not work well. So if parameters are optimized and the model is considered very well, maybe the performance is similar to existing linear model or some other models, but usually the prediction performance isn't really fantastic for this case. Yeah, do you have any questions so far? Yeah, so at least neural network is not for every analysis. And it applies to very limited cases. I'm working with the Michigan Department of Transportation project, and originally they asked some cutting-edge machine learning methods to analyze the public auction price for Michigan DOT projects. But we just mentioned the neural network or tree-based methods to show our ability to analyze that data. But it turned out that the sample size is only 1,000 or something. And also 1,000 projects are categorized into several different categories. So sample size is like 200 or 300 for each category. So, and we have many predictors, but we don't know which variable is useful. So in that case, usually the neural network isn't really promising method. Okay, so next, how to fit neural network. So we have parameter beta and W. So we have the parameter between nodes and input, and the output and nodes and between nodes. So how to estimate parameters? You can imagine that this is very nonlinear problem, because the relationship between nodes and input is basically the logistic curve, or a somewhat complicated curve. And nodes and nodes, if we have two layers of nodes, the function between nodes, relationship between nodes, is also nonlinear. So it's very complicated function. So if logistic regression is only, just if only there is one logistic regression model, then we have convex. We have convex, the loss function, but the neural network, it's so complicated model. So we cannot really guarantee the finding the global minimum of error function. And also remember that if we have multiple nodes, if we have input and we have output and we have multiple nodes, then we can see that these three nodes are not distinguishable, because these are just the intermediate steps of neural network. So there is no way to distinguish these three nodes. So that means the parameters are not identifiable. So if the parameter for this is 0.1, this is 0.2, and the parameter to this is 0.3, and this is 0.4, if you switch this 0.2 with this 0.4 and this 0.1 with 0.3, then also we switch the parameter here and here. Suppose this is 1.2 and 1.3. If we switch this, then we got exactly the same result. So we have multiple global minimum for loss function. So we cannot really identify it. So usually the algorithm for neural network focuses on the value of the error function. So just the error function that changes from 150 to 141 to 132 and 130, 129, and so on. So just we see the value of the loss function, not really that we are seeing parameters. So maybe the original parameter space are here, then maybe 150 is here, but the 141 is here. And maybe 132 is here, and 130 is here, 129 is here, or something like that. We don't really see how parameters are moving. So we just focus on this number, the value of the loss function. And if it stabilizes, if this becomes 128.5 and 128.4 or something, and yeah, it stays the same for several iterations, then we just see this as convergence. So this is pretty unstable method because also we will discuss it later, but some algorithm is random, stochastic. So the estimation result isn't really the same for each simulation. So if you estimate once, then you estimate it again, then result may be different. So that is the very unstable characteristics of neural network. Yeah, and how to optimize neural network parameters. So basically, we use the least square method. So we minimize the sum of squared errors. But this f, the function for neural network, is complicated like this. Remember that G is link function or activation function in neural network. And we have basically the linear combination of parameters, then activation function, then linear combination again. If multiple layers, then we have more functions, maybe G of this, and again, linear combination, and so on. But in general, you can say that this is the objective function and we want to minimize it. And suppose theta includes all parameters. Then the usual method is just similar to Newton-Raphson method. So we think about the derivative and we go to the direction that the objective function makes smaller at the fastest speed. So we take the derivative for each parameter, then we go the direction of the most, the steep direction of parameter to make the objective function smaller. Yeah. So usually in Newton-Raphson method, that we just see maybe in Newton-Raphson method, this is theta, then this is the final objective function. Then usually we just use slope to get the next one. So suppose that we start estimation at theta 0, then next candidate for theta is this, theta 1. But we don't go this much. So for neural network, that we proceed only slightly. So if rho is 0.1, that we go just 1/10 of the entire amount. So we go just gradually. So that is the parameter rho. So we have the learning rate. Actually, rho has different meaning in our implementation. That's here that we write parameter rho. In R, the learning underbar rate is the parameter's name. And this method is called gradient descent. So we gradually approaches to the optimal point. So in this case, this theta, if we update theta 7 times, it reached the global minimum. Sometimes it reached to some local minimum so that it does not converge to the, it does not converge to the global minimum. And we cannot really see this graph in neural network. We only see the value of R of theta. And this isn't really important in this textbook, but this explains the further about estimation. So how to estimate these betas and these W's. And yeah, this is the function to get, to minimize. So we have to get the derivative with respect to beta 1 or beta 0, or maybe beta kj, wkj. And actually, when we use the chain rule, we can decompose these ones into several terms. Yeah. So this is called back propagation because when we have, for example, the 2 predictors and the 3 nodes and the 1 output, usually the updating parameter goes backward. So if we have this parameter, this parameter, this parameter, and this parameter, and this parameter, and this, and this, and this, and this, usually calculation was done for these parameters first, then after that we get these parameters. So we go backward. So yeah, so many parameters. So just I say this is the first step and this is the second step. So we update parameter backward. So that's why that we say this as back propagation. So this does not really affect. We don't really need this knowledge to tune hyperparameters, but this is the algorithm to do that. And regularization, neural network often overfit the data. So sometimes that we use this penalty term. This is similar to rich regression. So we use the rich regularization for neural network. And this is the just the log likelihood function for categorical case. Or 10 category response. So if the response is continuous, this function is just like RMSE or any other function you want. And yes, if the number of categories are different, this number may be different. Yeah, so this is basic concepts of the estimating neural network. So we optimize parameters. We have hyperparameter lambda. We have hyperparameter, maybe some other hyperparameter, maybe rho, and so on. Yeah, and the next one, the stochastic gradient descent. So this is just the optimization procedure, so more advanced optimization procedure. So we have done the gradient descent method, but here we have the stochastic gradient descent method. So to improve the efficiency of estimation, we use a small fraction of randomly selected observations called a mini batch to apply the gradient descent. So gradient descent, if we have, suppose 100 observations, maybe in this case, maybe, okay, so 50,000 observations, then you can, of course, use these 50,000 observations to update the parameter. But usually the people do this as more like online algorithm. So we just separate this 50,000 observations into 500 sets of 100 observations. So the batch size is 100, and we make the 500 batches out of these 50 observations. And we apply the stochastic descent method with these 100 observations. I'm not an optimization person, so I don't know why this works better than gradient descent. But usually we have to optimize when we have to optimize the function. The local minimum, so reaching to local minimum, not global minimum, is a problem. And if we have some noise, then sometimes that we can go out of local minimum. So for example, if we have theta here, just one-dimensional example, and we have this kind of objective function, error function, then if the algorithm is very stable, maybe if we start from here, just go here, and reach this point. Sorry, I think this graph is not good. But sometimes we miss the global minimum. But if we move more, like this and this and this, this and this, finally we have higher probability to reach to the global minimum. So I think probably this is the reason that we use the stochastic algorithm for this. Yeah. And so basically we run 500 updates for full data set, but we repeat this 500 times procedure several times, for example, 200 times. So each of the procedure is called epoch. So one epoch consists of 500 batches of 100 observations each. So we typically use the hundreds of epoch to get the estimation. So that means we use 50,000 observations 200 times.
They say they're used randomly or chosen randomly. Is that random with or without replacement?
Random without replacement for this case. Yeah.
Thank you.
And it is, yeah. So that's it. And the another positive aspect of this the stochastic gradient descent is that it enforces its own form of approximately the quadratic regularization. So we update again and again, right? So that means it can avoid some overfitting, right? So sometimes when we try one more epoch, the result gets worse. That can happen. So so if we increase the number of parameters infinitely, then it always, the training error gets smaller. But the neural network algorithm, since this is stochastic, so sometimes the error gets larger when we update epoch. We do one more epoch. So that is approximately similar to regularization. So the SGD, the stochastic gradient descent, is basically includes some kind of the penalty for complexity. Yeah, so that is one good feature of SGD, so it automatically avoid overfitting in some way. And here is the example. So when the number of epochs gets larger, then what will happen? So this is the number of epoch on x-axis, and this is the value of objective function. And yes, so this is the value of classification error. So classification error and objective functions are similar, but often objective function is likelihood based, and the classification error is just the number of the errors, so the count of errors. So it's slightly different, the criterion, even though these are conceptually similar. And so basically this graph and this graph are similar. And this orange one is the validation data set, and the blue one is training set. So for training set, usually we do iteration of many epochs, then error size that gets smaller and smaller. It fluctuates a little bit because of some noise, maybe stochastic feature of the program, but basically it gets smaller. And for validation set, actually it really depends on the case. It really depends on the case, but it gradually decreases and finally stabilizes. That is the best scenario. And sometimes maybe this case is also true. So it decreases somewhat, but after that it increases somewhat. Like sometimes clear the increasing trend here. So you can see some optimal point. So epochs is the number of epochs is kind of the amount of experience. So more experience, it's basically better. But based on some parameters, sometimes this tends to overfit the situation. So when overfit, we have several things we can do several things. For example, we can make the regularization parameter larger, or we have studied dropout. So dropout also avoids the overfitting. So we make the dropout parameter larger. Then we hope that the curve of validation set error stabilizes rather than increasing. But sometimes this method does not work. So dropout and also regularization parameter may not work in some cases. Maybe this orange curve becomes monotone decreasing function, but it does not become as small as this. So in such a case, sometimes people just stop at some epoch. So in this case, if we stop at 7, then maybe error is smaller than having the larger number of epochs, such as 25 or 30. So that's called early stopping. So it's pretty arbitrary method, but sometimes people do. Yeah, classification error, basically the same. Basically the same, yes. It's just a slightly different, the objective function, slightly different function from objective function. So classification, the likelihood, so objective function is minimum, so that does not mean classification is minimum. So it depends on the penalty on outliers or some other criterion. And here the dropouts. So dropouts, in each so for each batch that we do not allow to use several parameters, and we assume that several parameters are set to be 0. So the method is to randomly select a certain percentage of the dropout. So in this case, maybe 25% dropout for this first layer and 40% dropout for the second layer. And we do not allow to use these nodes. So that means when we estimate parameters, that we assume that all parameters are 0 from these gray circles. So this parameter is assumed to be 0. This is 0, this is 0, and this is 0, this is 0, and so on. So this sometimes avoid the overfitting and that makes the test error smaller. And it sounds in our the Keras package, the dropout rate can be chosen for each layer of nodes. So this is the summary of the hyperparameters. So I think the most important one maybe is the number of layers. So we have maybe 5 nodes in the first layer and 3 nodes in the second layer and a third node in the third layer. And this is the output and this is input. So this structure, so like the 5-3-2. So this is probably one of the most important, the selection of parameters. And also activation function. So activation function determines the relationship between nodes. And in Keras package, you can use, we should use the same function for each layer, but for different layers, we can change the function. So you can choose, for example, arctangent here. Sorry, the hypertangent here, and here maybe a ReLU function or something like that. So we can differentiate. And the learning rate row. So learning rate usually does not affect much the estimation result, but in neural network, if learning rate is too large, this the curve is too volatile. So this orange curve suggests the learning rate may be too fast. So for example, when we see the result, yeah, so you want to use probably this point rather than this point, right? But this fluctuates too much. So the last one is probably the worse than the asymptote. So it's too noisy, so that sometimes we are unlucky to get a larger error. Sometimes we get the too small error. So if we want to avoid this kind of the zigzag pattern and want to make it smooth, learning rate should be smaller. But also that if learning rate is too small, sometimes we cannot go to the global minimum. So update size is small. So sometimes we are stuck in a local minimum. So sorry, the large learning rate and also small learning rate has their own problems. And batch size, I'm not exactly sure how to choose the batch size. Probably this is not really that important parameters. When the batch size is too large, I got some warning. I don't know why. Maybe each the gradient descent step is too similar, so that we have some trouble. I don't know, but the batch size probably does not matter much. And the number of epochs, so number of epochs is just the number of epochs. So as long as it converges and the fluctuation is smooth, then that should be fine. So basically larger epoch is better. Larger is better, especially except for early stopping case. So this is almost tautology. So larger is better, except for larger is not better. So if not, then early stopping is used. And regularization parameter, actually the textbook does not discuss this much, but this is certainly another parameter. So maybe I should say that this is another important parameter. So maybe I should put here. And the dropout rate phi. Yeah. And regularization parameter, dropout rates. So these are both for avoiding overfitting. So sometimes we don't tune all parameters, just we choose one of lambda and phi. Yeah, so that's the case. Yeah, so this is the basically the everything about the algorithm discussed in this section. So we can choose these parameters to get the better forecasting performance. Any questions? And the last section is very short section. So this is strange, but this is about interpolation and double descent. Interpolation is just the concept of fitting a perfect model. So if we have 100 observations and we have 100 parameters, then the basically training error becomes 0. Because 100 parameters explains the 100 observations in any situation. And usually this interpolation is not good. Usually it has the severe overfitting. If we have 5 observations and if we fit the degree 5 polynomial, always we can fit this well, but usually this is overfitting. But sometimes interesting phenomenon called double descent happens. So just you can see the graph. So this is the degrees of freedom, and this is the error size of some regression problem. And the training error is orange and the test error is blue. And the training error, of course, gets smaller when we have more parameters. So I think this is the case for 20 observations. So when n is 20, actually the error becomes 0. And test error, we have some optimal point, probably around here. Around here. So this has the smallest test error. And then it increases. But actually, when the degrees of freedom becomes much larger, then actually test error gets smaller again. And this point is not as good as this point, but still it's somewhat small. So yeah. So this sometimes happens. Yeah. So this is another graph showing this phenomenon. So this is actually from the same model, but in different representation. So this is these circles. Black circles are observations, and the black line is the true curve, and the yellow line is estimated curve. And we have the number of parameters here, 8 and 20 and 42 and 80. And it sounds that 8 is the optimal case. So this is very good. And 20, this is obviously overfitting. So usually we quit analyzing the model. Okay, so 20 is the maximum possible number of parameters, and 8 is the best. That's it. But actually, when the number of parameter becomes 42, okay, so this is overfitting, but the better than 20. So 20, I think the curve is too volatile, but the 42, it's somewhat reasonable. And 80, it gets worse again, especially maybe here and here. But still slightly better than 20. So sometimes, okay, so 8 is optimal. 8 is optimal, but the 42 maybe next, the second best. So that can happen. So this is called the double descent. And the double descent does not always happen, but sometimes it happens. I don't know if this is useful or not, the useful concept or not, but sometimes it happens. Okay, so that's it. Do you have any questions? Okay, so I think we only have 5 students, and probably all of you make a presentation in my past class. So I just briefly discussed a guide to final presentations. So this time presentation is 12 minutes, but we only have 4 presentations per day. So the time is more flexible this time. So I would say 8 to 15 minutes. And this is a statistical presentation, so just follow the format unless you have special reasons. So introduction, the briefly explain background in layman's terms. So don't spend too much time, just briefly explain the background and explain your objectives. And data description, and what's the data source, and what's the meaning of variables, and sample size, and other essential information, especially if you use data from data repository or data competition websites, then be careful to interpret data well. So don't ignore the meaning of data variables. Then you discuss methodologies, explain the theory behind the model if model are not discussed in the course. Then empirical results. So at first, descriptive statistics and figures. So the former professor at Wayne State, Professor Sun, mentioned that the 90% of insights are obtained by descriptive statistics and figures, and only 10% came from statistical inference. And probably this amount, 90%, gets smaller for data, machine learning, because model is more complicated, data set is larger, more variables. So some patterns cannot be detected in descriptive statistics or figures. But still, the descriptive statistics and figures are important in most of the projects. And to demonstrate and interpret empirical results and its implications, and to interpret the estimation results as long as it's possible. So yeah, sometimes you cannot interpret the parameters, neural network, random forests, support vector machines, we cannot interpret it. But if you use more basic models, you can interpret it. So just make some interpretation as long as it's possible. Then conclusion and summary. Yeah, so slides, my recommendation is 12 to 20 slides for 12 minutes presentation. Yeah, so make slides readable. So use large font. Large fonts. I think the last semester, the biggest problem is most students use small fonts. Almost no one can read slides. So that is a problem. So maybe this is possibly most important. And avoid R code and the raw R outputs in your slides. If you just put the R outputs, then it takes more time to interpret. So just make more organized tables and the equations. Yeah. Yeah, so that's it. And if you don't make a presentation, then you cannot get credits. So this replaces final exam. So the policy for final exam applies to this presentation. And practice twice to make it on time. Yeah, so yeah, maybe other things that you can see. Finally, I will ask slides and also R code. I only read R codes when I have some doubts in slides. For example, procedures are not correct or something like that. So you don't really have to make the R code beautiful, but just attach it. And yeah, grading criteria. So are these. So meaningful of objectives, meaningfulness of objectives, and the clarity of introduction, quality of data, appropriateness and clarity of statistical methods, demonstration and interpretation of results, and the votes by classmates. And the schedule is here. Yeah, so that's it. Do you have any questions? I haven't reviewed the final project plans for the last day. I think the most of you have already talked to me about final projects, and you should be fine. Yeah. Do you have any questions on final projects? Some sample project slides are available on the internet. Those are 3 presentations last year. Yeah, I picked, I think, the best 3. Last year, actually, the quality of presentation do not differ much. In some years, some presentations are really excellent. Some are not really. Last year, the quality is pretty similar, but still some are better than others. So you can check the sample presentation slides. Okay, so if not, if you don't have any questions, then we go to the R implementation. Next time, probably we do some exercises. Have any of you have installed the Keras package into your R?
I've installed Keras on the Windows side. I have not yet
Run the code.
brought it into R yet.
Mm-hmm.
So I'm getting close.
Okay, so others? No, I think that you can try. And it may be hard. And if you cannot install it successfully, don't worry too much. But in exercise, you cannot really run your code. So I hope some of you have installed it successfully so that we can discuss it on Monday next week. So usually I make groups. So if the one of the group members have successfully installed the software, then that should be fine. And I don't ask more quizzes. So if you cannot install, maybe you lose just 2 points in the daily quiz scores, but that's fine. Of course, if you use neural network in your final project, you have to install it. But otherwise, yeah, hopefully you install it. But if not successful, don't worry too much. Yeah, and I'm using M1 MacBook. So MacBook with the ARM processor. So if you are using the same environment, you are lucky that the GitHub page have pretty comprehensive guide. So basically, you just have to cut and paste the code to the terminal on your Mac. Then everything will be done. Yeah. And yeah, we discussed this, and we discuss in this section the hitters data with 263 observations. Oh, sorry, the original data set has 322 observations. And if we omit NAs, rows with 1 or more NAs by using this NA.omit function, then we only have 263 data points. So it's 19 predictors and 1 response. So response is salary. And this is the histogram of salary. And obviously it's skewed, like chi-square distribution with DF1. So yeah, but it's natural that at least in United States, the few people have extremely large income and the most people have low income. Still 500,000 here. But statistically speaking, the log of salary is a better variable to predict. If we fit linear model with these data with original salary scale, basically these observations dominate the result. So this is better data. So I decided to go with the log of salary. So it's slightly different from with textbooks example. And the 1/3 of data is test set and 2/3 training set. And X and Y are just the X is a set of predictors and Y is response. Log of salary. So I added log of salary to original data set, and I excluded the salary from the original data set. And baseline, linear model with step function. And these are selected. It's pretty good. Actually the 1, 2, 3, 4 of the 8 selected variables are significant. And at bat, negative coefficient, it's strange. Number of hits, more hits, a better player. And the walks, yeah, hits are most important variable. And the number of years also affects. The longer they played, higher the salary is. Division, the Western or Eastern, we have some variables which may affect. And the log scale, so the meaning is less clear, but the typical error size in terms of mean absolute value is 0.6. So we have taken logarithm, so that means the typical error is the exponential 0.6 times larger, or exponential negative 0.6 times larger, maybe. So e to the power 0.6 is around 2.718 to 0.6. So this is around what? Square root, then maybe 17. So I don't know, 1.9 times or something. So the prediction performance isn't very good, but the maybe salary is, yeah. So estimated salary is maybe if the $1 million, then maybe we can say that maybe the actual salary is the 1.9, maybe 1 over 1.9 to 1.9, maybe something like that. And pipe operator in R, percent larger percent. So this represents the so basically this passes the previous term as the first argument of the next function. So here is one easy example. So okay, so at first the pipe operator is in some packages. So one is Keras and another is what, I forgot, but the several packages include that. Some graphics package includes this. And yeah, library Keras, then we define this as a z vector, 1, 2, 3, NA5. And we can take the average of this with NA removed as the mean of z, comma, NA RMT. So this is the average of 1, 2, 3, 5. 1, 2, 3, 5 divided by 4. So this is actually equal to 2.75. It can be done by this way. Sometimes it's convenient. Yeah. And the neural network, now how to fit the neural network. At first, the model setup. So we use this Keras model sequential model to model the neural network. So basically, we can make multiple layers by specifying each layer, specification of each layer. And layer dense is basically one layer of nodes. And here we have the unit 50. So we have 50 nodes. And activation ReLU. So that means if we have input layer here, then, okay, so this relationship between input layer and the node is ReLU. So ReLU function is, this function, right? So the piecewise, the linear function. So this activation is used. And this is a kind of strange one, but for the first layer that you have to specify the input shape. So this is number of columns of the X, so the number of variables. And other layers, we don't really have to specify like this. And for each layer, we can also specify the dropout rate. So this is 40%. So we have 50 nodes, but each time we only use 30 of the 50 nodes. So this is model setup. This does not estimate it yet. So this only includes the general model specification problem, and it doesn't include any data. Maybe I use X, but the number of columns of X is just a scalar. So it does not include data yet. And then we specify the optimization method. What function to minimize and what optimizer to use. It sounds RMS prop is not stochastic descent method. So it's similar to, I think, the usual gradient descent method. I don't know exactly, but we have several options to estimate. And loss, we have any function. We can define any function. And here, the mean square error is minimized. Metrics, this is the final error function that to be expressed. So in this code that we minimize MSE, but we use MAE, mean absolute error, as output. So we have some discrepancy here. Later that we fix it, but this is the textbook's example. Then finally we fit. Then the calculation starts. Maybe it takes 1 minute. And we specify the number of epochs and the number of the batch size. Sorry, the batch size. Then this is validation data. So each time, actually, they calculate the test error. So we shouldn't see the test error to choose the model. So maybe we have to be careful, but we can see the test error size at the same time as estimation. Then the plot of this history one, then this. So this is the training error and validation error. And this is loss function, and this is MAE. You can see that this converges to sum. So it does not suffer from the overfitting. And you can see the validation error is larger than training error. That is natural. And we have some fluctuation here. Right? So because of the learning rate is not too small. So it fluctuates a little bit. Learning rate is larger, fluctuation is larger. Learning rate is smaller, fluctuation is smaller, but the convergence takes time. Sometimes it does not reach to the optimal global minimum. And yeah, so this is the predicted value. And this is MAE. And we achieve 0.45. Actually, when I run, that was 0.51 or 0.53. So it depends on the simulation. So each time the result is different. So that's why I put 0.5 to 0.6 typically. But this time we are lucky that we have 0.45. And it's a little smaller than the previous one. Do you have any questions so far?
Looking forward to trying it.
Mm-hmm. Yeah, and the next one, I try to optimize parameters. So we have only 19 predictors, and so I set 19 as the number of the nodes in the first layer. We don't have any specific reason, but that is usually a good starting point. So the number of predictors. Possibly it can be larger, can be smaller. And I prepared the second layer. Second layer, we have 5 nodes. Usually, after the first layer, we want to summarize data into the second layer. So the decreasing number of nodes works good in many cases. Sometimes makes smaller and larger, smaller, that works better. And also activation function. We can use many functions, ReLU, sigmoid function, the hypertangent, CeLU. CeLU is a kind of slightly smoother version of ReLU. So it uses exponential function rather than the piecewise linear function. So like this or something like that. And softmax function. So this is used for the last layer. So for categorical variables. So we can transform values into several probabilities. So like the P1, P2, P3, if we have 3 categories. So in such a case, the last one can be softmax function. And soft plus, this is just this function, soft sine, exponential, and so on. Yeah, and the dropout, yeah, so these are the activation function. Input shapes, this has to be assigned for only the first layer. And the dropout rate, the dropout here also. So we have 2 layers. So each layer we can specify dropout rate. But it sounds dropout does not help much. So I set just dropout rate is 0. Probably you can just omit this line as well. And the last layer we have just one continuous variable. So just one. I'm not exactly sure. I think that if we don't specify activation function, I think the no function is applied. So identity. And learning rate is default, is set at 0.001 as default. And yeah, larger or small, sometimes small learning rate, large learning rate have a problem. But when I adjust several times, it sounds for this case 0.001 is good. And we fit the model. Then this is the loss function, and this is mean absolute error. Oh, sorry, once more. So we use the MAE as loss function. So when we optimize parameters, we use this as objective function. So this is consistent with the final metrics. So we hope that the performance is better. So sometimes in logistic regression, if we optimize the deviance, then we found that error rates gets worse. But if these 2 criterion are the same, so it's likely that we have a better results. And it sounds that it converges pretty quickly, so I make epoch a little smaller. Even maybe 300 is sufficient. Then this is the graph of the validation error and the training error. And it sounds very small. So this is 1, so it's much less than 0.5. And actually we get to 0.36, so it's much smaller than the previous one. And compare the results. So this is the linear model. And this is the neural network without the parameter optimization. And this is neural network with tuned parameter. I didn't systematically tune it, but I tried several ones. And obviously, neural network performs better. We have higher correlation. Actually, the linear model, the predicted value, actual value and predicted value have correlation coefficient of 0.65, but the neural network, we have much higher, 0.82 or 0.80, maybe 81. And you can see that the difference between these two, actually not much different, but you can see that the majority of observations, this one has higher correlation. This has slightly lower correlation. But when we see some outliers, actually, outliers are slightly better in this model rather than this model. So you can see that the correlation is basically, squared penalty. So if the error size is large, error size is like this, and error size is large like this, the penalty is steep. But if we use mean absolute error, the penalty is not that large. So basically, this model focuses on the mean absolute error. And okay, so these 2 observations are not good, but others are pretty good. And this one, we want to avoid large error. So yeah, so these points are somewhat closer to these clouds. But within these, usual observations, error size is slightly larger than this. So this is the effect of the objective function. So this one, MA is objective function. This is MS is objective function. So this is more, this targets more like correlation, and this targets more like mean absolute error. So mean absolute error is smaller for this case, but the correlation is higher for this case. Yeah, so these are the neural network examples. So next time, hopefully I do some exercise. And no more quizzes in the future. I will ask you to comment on other presentations, but now that you can focus on final projects. And I will comment on the May 1st presentation plan by Friday night, or maybe technically Saturday morning. Yeah. Do you have any questions? Okay, so if not, see you next Monday.